things. I don't know. Maybe we're not right about the moon being completely dead. Despite being our closest celestial neighbor, there is cloud in history. In total, humans have only spent 80 hours on the moon. We have made a superficial inspection only of a tiny fraction of the surface.
דמי, אתה שומע אותי?
כן, שומע מעולה.
אני לא שומע אותך בכלל.
בכלל אתה לא שומע? Okay, if anybody else hears me, please say hi.
Hi.
Okay, so other people actually hear me.
Demi!
Hello! It's amazing to see how many people I haven't seen for a long time, and right now everybody are virtual. עוז, אנחנו באנגלית עכשיו, נכון? כאילו, אני לא טועה.
כן, כן.
Okay, cool. So I'll continue on speaking in English. I think we'll wait about 3 more minutes, and then Oz will take control and start the presentation. I'm actually recording, so we'll upload everything afterwards to YouTube. That's about it, I think. Anybody wants to sing, to create some kind of background music or something? Any volunteers? No?
Demi, maybe you sing something.
Trust me, you don't want me to sing.
Makes me want to hear you sing.
I'd rather really not.
This will finally explain the mysterious mix
The album.
Okay, I think we have around like 50 people right now.
Important is. Oh, okay.
No problem. We will join with the other meeting. Thank you.
and geologically active world, and this part escapes to the surface as gas. To find any sort of water on the surface of any world besides Earth is a huge discovery. Discovering water on the moon is like discovering gold, except it's much more valuable than that. This is the possibility of lunar life. Scientists believe they can use the moon's water to propel humans much further, much faster into space. Propulsion engineer Tim Pickett explains the principle of.
So basically, I muted everybody except Oz. And you can unmute yourself, but I think you'd rather like leave that unless you have any questions during the session itself. Okay, I think that people will keep on joining, but again, because we're recording, I really feel comfortable of actually like starting. And I will start with a really short introduction of where we're at right now. We're a part of the Big Things community, speaking about big data, data science, and DevOps, and all sorts of other cool things in software engineering. And welcome to the community, whoever wasn't here or in any previous meeting in the past. Also, I think Itai is with us, right? Itai, say hi.
Everyone.
Hello. Itai is also one of the organizers of the community. And today we'll be talking about data versioning tools. Oz will actually introduce himself once I give him the stage. And he'll tell us a bit about this world and different types of implementations and tools that are used today in the industry, and different types of approaches to that whole area. So I think, again, I won't talk a lot. And Oz, the stage is yours, and I'm muting also.
Okay. So first of all, thank you, Demi and Itai and everyone else who's involved in big things, making big things happen, pun intended, I guess. And also thank you all for joining. These are not easy times for many of us, especially like with the quarantine just around the corner. So it's my privilege to give you 1 hour of escape from all that going on and talk a little bit about data versioning, which you are all very excited about, I'm sure. It's pretty hard to do something like this over Zoom. At least for me, this is a first. So I will ask you, you can interrupt with questions if you must, but I think it's going to be a little easier if you save your questions to the end, and then we'll just have a little bit more of an open Q&A once I'm done with bombarding you with all the materials that I prepared. And other than that, I guess we can start. Okay, so let me just share my screen quickly. If you guys can hear me and you can also see my screen, please do this, just so I know I'm good. Thank you. Okay, so as Demi mentioned, I'll be speaking mostly about data versioning today, but I'll start with introducing myself.
Oz, 1 sec. Only the palette of the people, you can also move that from the screen for it not to hide your slides. That's it. Yeah, thanks.
I'm leaving just you so that I'll have some visual cue if I'm doing well. Okay, thanks. So yeah, I'll start with introducing myself. So my name is Oz. I'm the CTO and co-founder of a company called Treeverse, which was founded earlier this year, basically around January. So we were lucky enough to get started before the world went crazy. We are developing an open source platform called lakeFS, which I will soon present, so I won't talk much about it right now. Besides that, I've been in data and analytics and companies that have been doing stuff like that at scale for around 20 years now, starting from telecom to analytics companies and startups. I've seen a lot, we can say. And this whole talk is basically kind of opinionated, based around my opinions. So everyone is biased in a way, and this is my specific bias around data versioning. And I'll start by sharing the agenda. So what am I going to talk about today? So I'll do a very brief overview of the use cases for data versioning. There are a lot of tools and systems out there that say that they do data versioning, but they actually mean very different things. So I'll try to go over what these things are. I'll talk about lakeFS, which is the one that I'm naturally the most familiar with, and talk about why it's good for the world. I'll talk about what we get compared to the most, which is the data versioning formats. That's Delta or Delta Lake, Hudi, and Iceberg. And then I'll try to kind of combine everything back together and present a real world example of using something like Delta, but it's interchangeable with all the other formats, together with lakeFS to build something that's actually useful, which is a resilient data pipeline. An example that I think you might feel familiar with. So let's start. Let's talk about the use cases for data versioning. It's kind of hard to like put everything into neat little boxes. I tried to do that. Of course, there's some overlap between the tools, but the 4 major use cases for data versioning that at least I recognize are collaboration, ML ops or building ML pipelines, updating data, basically, having tables that I can update or mutate, which is not as trivial to do when we talk about big data, and managing the lifecycle of data. We have application lifecycle management, but we also have data lifecycle management for everything that's around the data itself. So these are like the 4 distinct boxes that I chose to present. So starting with the first one, so data collaboration, what does that mean? There are a few platforms. These are just examples. Kaggle, Build Hub, and Dags Hub, which are actually an Israeli company, and they're doing very cool stuff. Their aim is to provide a collaboration environment for mostly data scientists to be able to collaborate around shared data. And if I want to collaborate with someone across a different continent, maybe a different company, or even if I want to do it internally inside my own company, in order for me to collaborate around data, we need to agree on what data we're looking at. And this requires versioning. So Kaggle gives you kind of a platform to share public data sets. It also gives you kind of a nice environment to run them on like a notebook-like environment. So people can share their data sets along with like their Python code that does something useful with that data. This gets uploaded to Kaggle and it's then freely available for other people to use, to contribute, to fork and modify, which is really useful when we talk about public data. And then there's DoltHub, which is kind of a more integrated solution. So they try to give you a versioned database, which is pretty crazy, which does versioning like at the row and even the cell level. So everything I do, every piece of data that I mutate inside DoltHub is actually versioned. And they also have DoltHub on top of Dolt, which is the database, which gives like a more widely available collaboration environment on top of that. So they try to kind of do everything in one tool. And then there's DagsHub, which is basically like the GitHub equivalent of DVC, which we'll see in a second, which is also a bit more focused on machine learning and tries to do versioning on top of like my sample data and my metrics for machine learning and even my models. Provide an environment that they collaborate around that. So if I have a few engineers or data scientists inside my organization and they want to work on a common task revolving around ML, so DagsHub gives me that collaboration environment. I can comment and I can visualize and I can interact with the data with other people. So that would be the first one. The second use case is, I guess, more centered around machine learning and like how do I take something from idea to a model serving in production. And these tools are like more narrow in their focus. They're only talking about ML data, which tends to be a little smaller usually. So I have like sample data, and then I have my metrics, and then I have my logs, and eventually I have a model that I want to serve. So these tools, MLflow, also Kubeflow, Pachyderm, and DVC, they're more focused on that. DVC is an interesting one because it tries to actually use Git for versioning. But instead of like storing huge files in Git, which is a huge pain if you ever tried to do that. So DVC will actually store some kind of link to data that exists somewhere else, let's say on S3 or on a shared server. But the versioning is provided by DVC. And like their whole language and the way that they present things is, again, very centered around machine learning. So if I insert new data in, I can like pass metrics and arbitrary metadata that is related to my machine learning model into DVC, and then I get like free tracking just by having different versions and different commits of the artifact I'm working on. Yeah, so these tools are mostly focused on the machine learning pipelines. The third one, which I'm going to dig a little deeper into soon, is basically mutability. So one of the leading use cases for, I'd say, big data in general is what we used to call OLAP. And now we have like different cool names for, which I'm not going to share the buzzwords. But basically what it means is that I have very large objects that are usually like scanned or accessed sequentially. I'm not looking for a needle in the haystack. I'm looking to aggregate or to find something across a lot of data. And to do that, usually I'll use a columnar compressed format, some variation of that. I'm not going to go now. We can talk about it maybe in the Q&A of why we do that using columnar and compressed data. But the idea is that for analytics and for sequential access, it's a lot more efficient. The problem is that once I store every column separately, and once I compress these columns, and then I'll also usually store it on an object store, which is immutable in nature, I can't update it. It becomes really hard to make changes to that data, right? It's really hard to mutate it. So basically, especially Hudi and Delta Lake, what they try to do is kind of beat the forces of nature and let me trade off basically compute power and money in order for me to update something that inherently doesn't want to be updated. So I'll talk a little bit about these in depth in a second. And the fourth use case, which is basically what lakeFS focuses on, is the data lifecycle management. So lakeFS is not a table format like the other ones. It's a lot more agnostic to whatever is running inside the data that's actually being managed. The idea is to give some way or some tool that can provide a process for us to treat our data the same way we treat our code, right? So if I have a development lifecycle, it starts with me creating an idea, trying something out, maybe experimenting with a different tool or a library or an algorithm. I want to do that in isolation, like I have in Git. I don't want to bother anyone, and I definitely don't want to touch production at that stage. And and then seeing this process all the way up to something that's deployed in production and is useful to someone else. And this is what lakeFS focuses on. How do we make that process as streamlined as possible, as safe as possible, and to make mistakes as cheap as possible, so that I'm not afraid to touch the data because it might be shared by someone else. So let's talk a little bit about lakeFS and what it does. So the idea again behind lakeFS is to provide basically an atomic versioned data lake on top of object store, which is kind of a loaded sentence, and I'll try to break it down. Basically what it means is that lakeFS is a layer that sits between my application, and like if I'm looking at like the usual data lake architecture, then I have many tools that I use to either ingest or process data. So you can still keep using those tools if you use lakeFS. That's like one of our design goals. And the data itself is stored on some shared object store. It could be S3, it could be the Google Cloud Store, it could be Minio or any other type of cloud storage that I'm using, because it's cheap and it's scalable and it's great. So we don't want to replace that. And the idea is to create kind of a middleware, a layer between whatever application I'm using and whatever storage I'm using that just adds that versioning and those semantics on top. So you can think about it as kind of like a middleware or a proxy that lets me do things that are smarter than what I can do today. If I look at versioning in general, so the idea behind lakeFS is to expose something that feels and behaves kind of like Git, where I can create branches and commit, and I can revert changes, and I get these great semantics. But it also something that scales to like the size of a modern data lake, basically. It should be able to scale to hundreds of millions of objects and very large tables and data sets, but still keep those great semantics. And that's kind of the idea behind lakeFS. So what does it mean to add versioning on top of like my existing stack? If you think about it, like all these tools, what they have in common is that they're capable of communicating with the object store, right? If I take Spark, like out of the box, I get support for talking to data that sits on S3, for example, and that's true for most of the other ones. And we wanted something that will enable you to use lakeFS without now starting to modify or to instrument all my existing code and making sure all my applications support it. So the way lakeFS works is that it's basically API compatible with AWS S3. So as long as my application can talk to S3, it can also talk to lakeFS. But you're probably asking yourself, S3 doesn't support branching and committing and all that, so how does it work? So for that, we have like a little trick, let's say, where instead of calling my collection or my object directly, I prefix it with the name of the branch or the commit that I want to be looking at. This means that as long as I can control where my data exists, where the path of my data exists, I can now use branches. And of course, there's a complementary API that lets me do the commits and rollbacks and all that. But when I talk to the data itself, I have this very clean semantic of how do I address it. So if I want to take a production pipeline and run an experiment, I'll just change master in this example to experiment-spark3, because that's what everyone is doing nowadays. And it works exactly the same, only now I'm working on my own isolated branch. So how do we branch data? Like, okay, it's cool that I can create a branch and everything is now super easy. I just change that prefix and everything works. How do I create branches? What does it mean to create branches for data? So this is an example of like how it shouldn't look like. And this is from an actual Git repository that I won't share the name of. So the way we see it is that there are like 3 major use cases of how and why I'd like to version my data. I'll present the models that support it. So the first one is simple. I just want a development environment. I have a data lake. It's maybe, I don't know, a few petabytes in size. It's pretty unfeasible, let's say, to create an entire copy of that, call it staging, and keep it exactly synchronized to whatever my production pipeline looks like. But on the other hand, I don't want my engineers to experiment on top of my actual production data. Problem is, a data lake is kind of a fancy name for a shared folder. And it's one big mutable mess where everyone's working together. And I don't want an experiment to accidentally delete something that users actually rely on. So basically, I have three things I'd like to accomplish. I want to be able to experiment, maybe try out Spark 3 without interfering with everyone else. I want to be able to compare between versions. So I want to compare whatever I ran with the new version of Spark with the existing one. And I want to be able to reproduce, and to do this like with strong guarantees. I want to go back to a single point in time, see the data as it existed and the code as it existed. So I'll be able to have like a good starting point for whatever experiment I'm doing. And I want to guarantee that that point in time will never change. And this way I can iterate on a process. So what would be a branching model that supports experiments? So basically it's very simple. I can take my entire data lake or a certain repository or whatever size I choose to create a repository for, and branch out of the master branch. Let's say that master is what everyone is looking at. It looks like an S3 bucket for everyone else. I call it master, and that's like all my readers always read from master. But I want to do some experiment right now. So what I'll do is using lakeFS, I'll create a new branch that's derived from master. This is a metadata operation. Like there's no cost involved. We don't copy any data. We don't move any data around. But once I have this branch and I'm reading and writing from it, lakeFS guarantees that whatever I'm doing on my branch on the side doesn't affect anything that happens on master. So in my branch, I can try out Spark 3, but I can also delete half my data just to see what happens. And because this is only on the metadata level, I'm not actually interfering with anything that happens to my production pipelines, to my actual data. If everything looks good and I decide that I want to keep those changes, I can always merge them into master, which is also an atomic operation, and it also doesn't involve copying data. But if not, I can simply iterate on whatever change I'm doing. And if I'm not happy with the results, I click the revert button, and basically I'm back to square one. So if I take the Spark 3 upgrade as an example, I can take my algorithm as is, try out my luck, just upgrade to Spark 3 and see what happens. And maybe it fails halfway through, maybe it succeeds, but I'm not sure about the output. If I'm not happy with what I see, I click revert, I'm back to where I was. I don't even have to worry about which files Spark actually touched, what do I need to clean up after. I don't have to worry about any of that. Once I reverted, I'm back to whatever known state I was before I started. If I do want to see what was touched, I can simply do a diff between the current state that I'm in and the previous commit, and then I'll know exactly which files Spark actually created, which partitions, which metadata files. I can just simply see that as a diff. So now that I have a diff, I want to be able to actually compare the data, right? So maybe another example here would be, let's think about something simple. Let's say I'm writing Parquet files, which Spark, of course, loves. And I want to play around with the different compression algorithms. Maybe test out what's the difference between doing snappy, gzip, or no compression at all. How does it affect my runtime, the size of the data that I get out, the performance for readers, the time my job takes to run? I want to be able to compare all of these between different compression algorithms. So if I create an experiment branch for each such algorithm and then just run the same job with a different compression algorithm, I'll get a different data set that I can easily compare. So I can take my Athena environment or Hive or Presto, whatever it is I'm using to query my data, just point it at a specific branch, run a query and see what happens. At the minimum, I can get a guarantee that data is exactly the same, like the characteristics of the data weren't harmed by doing this. But I can also measure like the runtime or anything else I want to be able to look at. And this is something that, like, if I have to design nowadays without lakeFS, I have to think about like the different path that I'll be creating, the different data set that I might need to clean up afterwards myself. If it involves moving a lot of data, this becomes challenging. Like, we know that a simple copy, when you talk about large volumes of data, is like something that's not very trivial. But lakeFS kind of does all of this for me. I create the branch, I run it on that branch. If I'm happy, I can merge. If not, I just roll back and I'm back to square one. So that makes like the cost of mistakes or the cost of experiments much cheaper. Third use case is I want to be able to reproduce. So let's say I did introduce an upgrade to Spark or maybe one of my ETL jobs, and now something on production broke. Could be immediately after I decided to merge my changes, but it could also be days later. And now I want to be able to fix that bug. If I want to do it nowadays, basically I have to kind of push my new code to production and see what happens. And in the meantime, whoever is reading this data will see my experiments. But here I can create a reproduction branch that's derived like from the last known good state. And this guarantees that the data I'm looking at is exactly the data as it existed, let's say, last week. And if I add to the lakeFS commit metadata also like the git commit of the job that creates this data, I now get reproducibility. I have the exact data that existed at that point of time with the exact code that existed at that point of time. Now I can use these two as long as like my algorithm is deterministic to get the exact same result. And this is something that's really hard to do today because even if I know like what data I read last week, like we know this is a shared folder. This data might have changed in the meantime. Someone did the backfill or changed the schema or ran some job to kind of massage the data to fit its own use case. Like there are very many reasons why the data, like the historic data might change. But lakeFS ensures that you get an immutable, repeatable process that you can always go back to. So all of these talk more about like, how do I develop something? How do I go from like, I have some idea into being able to see like what happens if I actually run it. Now let's say that I've already developed something. Maybe I did upgrade to Spark 3, maybe I introduced a new source of data, maybe a new job or a new pipeline. And now I want to be able to have other people also enjoy this data that I've created or changed. And then there are all kinds of concerns that I have to worry about. Like, how do I avoid like littering my data lake with all kinds of like weird data formats that I don't want or weird conventions that I won't be happy about later? And basically, how do I prevent my data lake into coming into a data swamp, as AWS calls it? We have all kinds of formats and like the same data copied over and over again, and like it's a big mess and no one can find anything. So we look at it as kind of like, this is CI, basically, right? I want to do linting for the data, like maybe the formats or the metadata, maybe validate the data itself before it even enters my data lake. I want to be able to do all of that programmatically, basically to codify my best practices so that it's repeatable and it's guaranteed. So here are like a few examples to kind of get your mind going. So say I look at master as kind of my source of truth. For these collections that are managed inside lakeFS, master holds like the holy grail, the truth that everyone should be looking at. And now I want to protect master from all kinds of weird things that might happen to it. So for example, let's say I'm worried about PII or storing like private information about users. So I can define a pre-merge hook that says if someone tries to merge data into master, and this data has a column that is like user underscore email, I want to prevent that from ever happening. I don't want this data to ever arrive on master unless it's under /private or like some common prefix that I know that I'm like taking very good care of and my permissions are correct for it and I can manage it. Another common example would be like I want to enforce good formats for the data that I'm using. I don't want CSV, TSV, like JSON files all over the place. I want to make sure that if you introduce a collection that's supposed to be read by someone else, I want it to be columnar and compressed. So I want to make sure that only Parquet and ORC files are allowed. And maybe Delta is a format. Nothing else can go through. Maybe I want to make sure that like columns are only ever added to production collections, never removed because that breaks compatibility. All kinds of like different business specific requirements that I have for the data itself. Or maybe I even have like a registry for metadata that's actually useful. Like it records the owner and the SLA of everything. And I never want to have data on my master branch that is not first registered on that metadata repository. So once I'm able to like codify these practices, I can ensure that once I set those hooks in place, no data ever reaches master. Like no consumer can ever see data if it doesn't adhere to these specific standards that I've set. And this prevents my data from actually becoming that data swamp that we discussed. So now I have like a place, a point in time where I can like prevent stuff like that from happening. And I can do that without starting to limit like the permissions and preventing users from ever writing anything, like losing out on whatever innovation they might create. Because I know that I have these guarantees, and as long as someone adheres to them, they'll be able to write to master. They will be able to provide value. So the branching model here is actually very simple. So you never write to master, and like we can set a permission that says you can only merge into master. No one writes to it directly, and like a lot of companies do that for their code. So everything I do on my own branch, and then I have a pre-merge hook that says, like for this example, no CSV files allowed. So if I write a CSV to my branch, which I called new data 1, which is a very original name, and I try to merge it into master, it's going to stop me. It's going to say, you violated one of the pre-merge hooks. There is a random CSV file here, which is not allowed. And this way I can stop all those changes from actually ever being introduced into master. But we all know that like that's like a day zero kind of thing, right? So I don't, it's not every day that I introduce a new type of job or a new type of data into my data lake. But I do have recurring jobs that happen every day, and I do have streams that are written all the time. And sometimes the code doesn't change at all, the jobs don't change at all, but I can still end up with very bad data. And that's because like the world around us change. Like the most common example here would be, let's say I'm collecting like analytics events from my front-end servers, but one of the front-end guys introduced a bug. And now I'm only seeing like half the events that I had before, or maybe I'm missing fields that were like part of my schema before. Something changed around us. And I want to be able to catch that before like it reaches the consumer, right? Before the CEO looks at the dashboard and is like either confused or annoyed because it doesn't make sense anymore. So how do I do that? How can I first prevent bad changes? Even if it was introduced, how can I roll back, which is not that trivial? How can I ensure that like if I have related data in a few collections that are all kept in sync? And how can I prevent data quality issues from arriving? So this is an example of a branching model that would support a rollback. So in this example, I have my master branch, and then I have some continuous stream of data, let's say coming from Kafka or some other streaming source. And I want to be able to go back to like a point in time because maybe I introduced a bug or something in the data changed. I want to be able to kind of roll back. So Kafka already gives us this kind of semantic, right? I have an offset for everything that happens in Kafka. I can always go back to previous offset and reread my messages. But there is no equivalent offset for the data that's actually on my data lake. And here, if I do like an hourly commit even, or like a commit at a certain checkpoint, I can record, like just by committing, I have all the data that's in my S3 that's being kept inside that commit, but also like the offset of the Kafka stream I'm reading from, which means I can always go back to this point in time and see like the data on S3 as it existed, and also like the stream as it existed back in that point in time. And this way, I can always go back to whatever previous state I want to go back to. If I'm not talking about streaming, if I'm talking just data that's managed inside my data lake, it's actually much easier. I simply point all my readers or even point my master branch to a previous point in time, and bam, atomically, I'm back to where I was. That's a good known state. So I introduced a bug, something changed around me, I can always go back. And that's something that's kind of really expensive to do today. There's always an example that I like talking about, and actually I have kind of a post-trauma stress disorder from it. We had a job back in SimilarWeb where I used to work before that was like doing retention. And retention is always kind of a tricky thing, right? And I need to delete data. No one wants to delete data because if I mess this up, it's really hard to go back. And it's not always trivial. Like it's not always enough to say, just delete everything older than 30 days. Sometimes you have all kinds of business rules around that. And like this job, like every engineer that ever had to touch it, like he would start by sweating a lot and then thinking very hard before pressing the enter key. Because if I mess up retention, there's like almost no going back. And like this horror scenario did actually happen. And like we ended up deleting almost a petabyte of data. Like we had versioning enabled on the S3 bucket, like an object level versioning that S3 provides. But now you have to figure out like which objects I had before, what were the versions, and then like call an API request for each one of them to go back to some previous state. And just managing like all that housekeeping, that was kind of a nightmare. It took weeks to go back. Here, I can run this script like in an isolated branch. I can test it out, see what actually gets deleted, and then just roll back. Second one is what happens like if, as I said, the data or the world around me changed. All right, so maybe someone changed my collection library or whatever it is that's sending the metrics to my servers. And now I have only half the data that I had a week before. And that necessarily means that something went wrong, right? Because the world didn't change that much, but the collection apparently changed. So if I do all that ingestion in a separate branch, I can decide that before merging it into master, before merging like my daily job into master, I'm going to do a select from Athena just to make sure that like the numbers line up or they don't differ too drastically from the way they looked last week or yesterday or whatever makes sense for my business. I can do this validation. Nowadays, there are like a lot of companies popping up or projects that do data monitoring of some kind, either for ML data or for analytics, companies like Monte Carlo, and there are others. And they provide like the tools to do the actual monitoring itself, like to look at the data, understand its qualities, and to realize that something is different. But right now, if I run those tools, it's usually a little too late, right? Because the data already exists. It's already available for someone else to read it. And now, even if I realize that there is a problem, the CEO is already annoyed because his dashboard is suddenly showing a drop that never happened. And the amount of trust in our data is now suddenly diminished, even though we have monitoring in place, because we only find out in production that something went wrong. With lakeFS, we can introduce that hook just a second before something is actually merged and is available to others. This one is a little bit more complicated, so bear with me for a second. This is what we call cross-collection consistency. It's usually another source of problems. So what happens if I have data that's coming from like two distinct different sources, maybe Salesforce or Marketo, but somewhere in the organization, I have dashboards or I have something of value that uses data from both. Like maybe does a join between those two tables to show some insight. However I manage this data, let's say it's a daily process or it's a stream, it doesn't really matter. I only want to show this data to whoever is looking at it from the outside once I know that both these collections are synchronized. For example, they're already updated with yesterday's data. I don't want to end up with showing like only partial data because only the marketing data is updated and the sales hasn't arrived yet. And this is something that's really hard to synchronize today. And people build all kind of weird processes around that to try to make it work. So the way we see it is that it actually becomes kind of simple. Excuse my analogy, like with the fish and the rice and the sushi. I made this slide just before lunch and I was hungry. But the idea is that I don't want to look at like the sales fish or the marketing rice and separate. I want to be able to consume the sushi, like the combination of both. So I'll write my sales data to one branch, my marketing data to another one. And then on a leads daily branch, I'll do the combination. Like here, every time I get an update from either one, I'll check that I have both sources available and that they're synchronized, and only then I'll merge them to master. And this actually gives a very strong guarantee to whoever is reading the data from master. Like they can know that if they see marketing data from today, it necessarily means that they'll also see sales data from today. And this is a very strong guarantee. And this is really hard to accomplish today. Okay, so talked a lot about lakeFS. Let's talk a little bit about data versioning formats. Right, we talked about Iceberg, Hudi, and Delta Lake before. So let's dig a little deeper into those and what they try to do. I'll say up front, this is all like based on my opinions, of course. I'll try to do my best to kind of give you the full scope and the full picture as I understand it. But of course, I have my own biases. So let's start with actually the one that I deem as my favorite, kind of, Iceberg. So Iceberg was born from Netflix, which is basically like a table format that tries to work around all the problems that they had like with the modern data stack as it exists in many companies, right? So a lot of us have S3 as storage. We have Parquet or something similar as like the file type, the columnar file type, and then we use the Hive style partitions to kind of organize the data. And this actually at scale creates a lot of problems. Like modern object stores, they give you guarantees around consistency, and they might even let you append into data. But most of us are not using modern object stores. We're using S3 instead. So there's a need for workarounds for that. So Iceberg is basically a table format that tries to kind of avoid all those common problems that Netflix occurred and that apparently other companies are also seeing. And the way they do that is actually pretty elegant. So data files are still stored into my object store, which one I'm using. But instead of relying on like listing my S3 prefix in order to understand which data files I have, I actually store it in a manifest file. This kind of sidesteps the whole S3 consistency issue. Now, of course, I want to be able to update my data as time progresses, and I don't want to be rewriting those manifest files, which tend to be huge because I have a lot of objects. And for that, they created kind of a tree. Like I have a manifest list, which points to a lot of manifest files, and each manifest file points to a lot of data files. So I get kind of a tree structure from that. And those things that S0 and S1 on top are actually what they call snapshots. So every time I make some change, I'm going to create a new snapshot, which points to a new list, which then points to a set of many existing manifest files, plus probably a new one because I changed something around the data. And this is great because it avoids all the S3 consistency issues, but it also allows us to do other interesting things. So by doing this, we're no longer coupled to the way S3 stores like its partitions. I no longer rely on like the hierarchy of date equals something, day equals something, like that common partitioning scheme from Hive, which is actually pretty terrible in S3 due to like scalability reasons mostly. I can decide on whatever arbitrary partitions I want. It doesn't even have to be an actual field inside my data. It could be whatever I decided I want it to be. Like a single data file might even belong to several partitions and not having to be written a few times. Another interesting guarantee that I get from this is that basically by creating these snapshots, I now it's sort of concurrency control, right? I can have multiple writers writing to the same data set or the same collection. Each one is looking at a specific snapshot, so data doesn't change like under your feet. And from that, if I look at previous snapshots, I get kind of free time travel. I can look at data inside this table at a specific point in time. So again, it's not as focused as other formats on actually mutating the data itself, although there are like steps towards that inside Iceberg too. It's more focused on like big tables that are slowly changing over time, and they have all the scalability issues from S3 and Hive Metastore that exist like with the common way of doing things, which is a very interesting approach. So the second one, Hudi, and this actually has a lot in common with Delta as well, is also table format, but like there's a pretty well-defined goal here. We have data that's being stored in columns. These columns are usually compressed because they compress very well. And now I want to be able to somehow update them, either by like upserting new updates or by deleting records. This like all of a sudden became very popular, especially because of like rules like GDPR or the ones that make you delete like only a single user from your system, which is very hard to do when you look at columnar data. So the way Hudi works is that, again, it's a table format, like whatever system I'm using has to support that table format. And it allows some semantics of doing upserts and deletes. And it actually lets you choose between two evils here. Either I do copy and write, or I do merge and read. What this means is that either for every change, I'm going to create like a new small file that simply records the change, and then I have many small files. Or for every update that I'm going to do, I'm going to end up rewriting a whole file, like a whole columnar file, just to insert that change. So this is kind of a trade-off between whether I want to optimize for readers or I want to optimize for writers. It's expensive either way. So like even if you do end up using it, it requires quite a lot of tuning. And to their benefit, it is very tunable. Like you can do a lot with Hudi to play around like with the performance trade-offs. And AWS really seems to like it. Like they seem to be adopting it inside, like Athena now supports it, and like it's native on EMR. A more cynical person might guess that they're doing it because Databricks is a competitor and they're more focused on the other format. That's just my guess. And because Hudi allows us to modify data, so now we are not only like writing once and reading multiple times like we used to. Now we might end up having multiple reads and multiple writes happening at the same time. We now have to keep them somehow in sync. Like I don't want to see the changes that are currently happening, because if someone upserted a record, if I look at all the data inside some partition, I might see like the old version and the new version. Now I have duplications. So to avoid it, they introduce kind of like MVCC for databases, a way of versioning my changes over time. This is kind of a must if you want to support multiple writers. And just by giving like those guarantees of that every change happens in its own new version, versioning is kind of a side effect, possibly a good side effect, but like a side effect of having to update from multiple writers. So Delta, which we kind of tend to hear a lot about. So Delta is like a lot of the same. They don't regard themselves as a table format for some reason. They call themselves a storage format, but like the ideas behind it are kind of the same. So the way Delta works is that like I still have all the same partitioning schemes and the same Parquet files that I used to have, but I also have this Delta log that gets written and basically records what changes happen to my data over time. And then like very small JSON files so that writing them is very cheap and very simple. And then like one every 10 writes, Delta will say 1 second, and we just compress all those changes into one Parquet files. And that's the way it works. And every such JSON file is basically like monotonically increasing number, which provides versioning, right? So I can look at my data as it existed at 001, or I can look at it as it exists right now, which is the latest number. Here is 3. And I can use the last checkpoint to know what's the current state. Because this relies on kind of the ordering of numbers, right now Delta is actually, if you're using something like S3, which doesn't give like the atomicity that's required to do something like this, you're limited to writes from a single Spark driver. This is something I assume they'll probably try to like work around somehow, but it is a limitation. For Hudi, they actually use the current timestamp, which is a little bit more dangerous actually, because time doesn't really monotonically increase. In both cases, they try to kind of create an ordering of events over time in order to understand like which updates occurred when, so that they'll know what data to present to readers. So that was kind of a very quick overview of the 3. So as you understand, this is more about like how do I provide concurrency and how can I do like updates over time to data, which is pretty different from like what lakeFS does, right? So I understand why people tend to compare the two, but actually it's 2 different use cases. So like to finish, I wanted to show maybe a quick example of how I can use something like Delta along with lakeFS to build a single pipeline. So let's start by like introducing a problem. So in this case, I have, we can look at it as multiple collections, but actually it's the same logical collections. And this is something that's like very common on data lakes. I have sales data coming from Salesforce. And for different like read purposes, I might want to partition it by 2 different schemes. So like I want to partition it once by date, because I usually want to look at like the latest data that arrived without having to query everything. But I also want to partition it by country, because in some cases I'm only looking at like a local aspect of my sales. And of course, something like Delta lets me update those partitions kind of in place. So Delta is a good solution to keep these 2 up to date with the stream of changes that's coming in. And now I have 2 collections, one that's called sales by date and one that's called sales by country. They represent exactly the same data, they're just partitioned differently. And then there's this poor analyst who's trying to understand how many sales we had in total. A very simple query. And in this case, sales by date is already like at its latest point, it's representing all of yesterday's sales, but sales by country is still being written to. Like I still haven't finished processing all the sales from yesterday into that collection. So now, depending on like how my dashboard is configured and like how this query chooses which partitioning scheme to use, I might get different results looking at the 2. And this is something that's you don't really want, right? Because you might even have one dashboard in the organization that's showing like a drill down by country, and it's going to use the second collection, and also like the total sales that were yesterday. And if I sum up those 2 graphs, I would get different numbers, which is really confusing and basically wrong. So of course, Delta allows us to update those collections in place, and it even lets us do like kind of time traveling inside each one, but there's no way to like synchronize the 2. So how will I solve it using something like lakeFS? So basically, I'll try to write those 2 collections inside one single branch. Because I know these 2 are related, I want to treat them inside the same branch. And then I'll coordinate my processes in a way that only once I finished writing all the data to both, I'll atomically merge those changes into master. So if I'm looking at the master branch, I'll either get yesterday's data for both collections or none at all. So there's no way like that my dashboards will be out of sync. And I can even go one step further and say, okay, it's nice that like my Airflow job is doing that merge. I can actually even create like a pre-merge hook to prevent anything else from happening. Like I'll introduce a hook that does this select sum from sales. And only if the results are the same, the exact same for these two collections, will I be able to merge into master. And this gives my readers a very strong guarantee around the consistency between different collections. This is actually like if I look at the real world example, I'm usually not even looking at one single logical collections, right? I have this star schema or snowflake schema or whatever it is that's modern to use today. And I end up, my queries tend to look more like this, right? I'll join other tables, I'll enrich my data with other stuff. And then if I want to look at a single point in time, I can't really understand like what's the correct point in time to look for each one of these tables. But if all these changes are merged into master on lakeFS, I can now say, show me this commit that represents yesterday, and it's going to be the same data over and over again because the data is immutable, right? So I have like this really easy way to synchronize different collections to a single point in time. That's it. That was a lot of information. I didn't have much time and I wanted to go over as much as I can. I'll share the slides right after the talk. You can read more about lakeFS. You can check out the docs. Of course, please contribute or at least start the repo and check it out. Contributions are very welcome. And from here, questions.
There was one question on the chat. You can see that if you have an auxiliary screen or something.
And just stop sharing for a second so you can see my pretty face. Okay, so the question is, does it mean we copy the entire key for each version of a commit for transform? Is the validation incremental or on the entire key? Okay, that's a good question. So the way versioning works with lakeFS is that unlike Git, which deals like with very mutable information, right? Code is very mutable. I update the same file over and over again, and it makes sense to merge changes inside one file. It doesn't really make that much sense to do something similar for data. So the way we look at it is that if you created a new object, it's going to be reflected in the version you're working on now. And if you now decide you want to create a branch or do a commit, all we do is create another pointer to that object. Right? And this is something that's metadata only. So it's going to be very, very fast. Okay, so even if I have millions of objects, but only like a few of them changed inside the commit, all the other objects I'll get from whatever previous versions I had. So like the entire magic behind lakeFS is that when you request a file, whether to read, write, or list, what we do is we try to say, okay, you're asking for the master branch at this specific commit. Which actual data from S3 should we be returning for that version? And that's like the entire magic behind it. The secret sauce here is how do we scale it to hundreds of millions of files and like very high throughput. Okay, second question from Guy. Does it work with Minio? So like we don't continuously test with Minio at the moment, but we have played around with it. And because it's actually API compatible with S3 as well, it should work. So if you have Minio, if you use Minio inside your organization, I'd love for you to actually check it out. And if there's anything missing or even tests that you want to contribute, that would be very welcome. I think that's a pretty awesome use case.
I want to intervene and ask a question. Infrastructure-wise, okay, because maybe I missed that. All of these pieces of infrastructure, even lakeFS, they rely on object storage.
Sure.
And can you like, maybe it's an overlaying layer, and can you combine different buckets of object storage layers? For example, for resiliency, or maybe even you have that distributed across like multiple cloud providers. So architecture-wise, how it's assembled, this is the most important part, because again, a lot of problems of object storage solutions, once you have a lot of keys, there are a lot of performance problems, and that's basically that.
Yeah, that's true. And I think actually S3 is probably the worst offender here.
I won't say, but whatever.
I will, that's fine. So the way we do it is that we try to be as agnostic as possible to the underlying storage. Right? We want the storage to do one thing and do it well, and that's storing the objects for us and letting us address them using a known key. We don't want to rely on the object store to do all the metadata operations, because historically they're not very good at doing that. Either it's consistency issues or just scalability issues. We store and manage the metadata for this ourselves. One reason is because basically we have to, because S3 doesn't know about branches and commits and all that.
No, of course.
And the second one is we don't want to rely like on the quirks of the individual object store beneath us. So we don't want to start like chasing around S3 and its consistency issues and trying to work around that. We simply manage the metadata ourselves. This way, whatever object store you have underlying, you're going to get the exact same guarantees. Listing will be strongly consistent. Performance will be at least as much as possible kind of within a very small SLA. The idea is to kind of like sidestep this whole entire metadata management area and basically bake it into the product itself.
And again, can you combine multiple providers in that context? Because probably you'll be running some kind of metadata server of lakeFS or whatever somewhere. And there is a web UI, I'm guessing, again.
Yeah.
So for that, you need to host that somewhere and have some kind of connectivity. And again, when you're talking in that context, the put and gets and all of the network and bandwidth that you're actually like doing there, this also might cost a lot if you're doing that on multiple cloud providers, for example.
Yeah, so as I said, because we try to be as agnostic as we can to storage, so running lakeFS basically involves three things. You need a lakeFS server that's actually handling the request, serving the UI, doing the S3 gateway API thing. You need an underlying storage bucket that could be S3 or it could also be VCS nowadays, somewhere to store the objects themselves. And then for like the persistence, we use Postgres, which you can easily get like from Aurora, RDS, wherever it is. So like the actual lakeFS server is completely stateless. We support Kubernetes as kind of a first-class citizen. So we have like a Helm chart on the Helm Hub already. The idea is to make it as simple as possible to run it on whatever cloud it is you're using. And if you really want to run on Google Cloud, but actually store the underlying data on S3, if you're crazy enough, you can do that.
It costs a lot.
Yeah, it's going to cost a lot in traffic. But if you're running inside like your own cloud, actually like egress costs are like very high on cloud providers nowadays. But if you look at the internal networking, especially in the same AZ, it's usually cheap. It's usually even free.
I agree.
You can get like a spot instance on AWS that has like 10 gigabits or even 25 or even 100 gigabits of network for pretty cheap these days. Like Moore's law is kind of over, so CPUs are not getting faster, but the network actually is. So like the actual cost of like transferring those bytes is actually pretty small.
I agree.
So a question, have you done tests on the scalability of this solution? I mean, I'm particularly asking because if the metadata is stored in Postgres, could that potentially be a bottleneck?
So yeah, that's a very good question. So like we have, and like the whole idea here is to target those who actually require those complex environments and need branching, and those tend to have a lot of data on one hand, and they need a lot of throughput. So we want to be able to support both. And actually the way we use Postgres is kind of unique, and soon we'll release like a blog post on how we actually do it. But like in our tests, we've managed to do like hundreds of thousands of operations per second across repositories that consist of several hundreds, millions of objects on a pretty modest RDS instance behind it. So the idea is like our whole aspiration here is like to squeeze as much throughput and as much scalability out of the system, because it is another layer that you want to maintain and you don't want to worry about lakeFS scalability, right? You want to get stuff done. So we'll keep improving that. The more use cases we have, like the more large installations we see in production, the more we can fine tune it. And here, like we're really thirsty for this input. Like lakeFS is slow for this specific use case because then we have something that we can actually improve. But again, I wouldn't worry too much about RDS becoming the bottleneck because of like the specific way we're using it. Hope that answers your question.
And another question actually about I would say synchronization, because the object storage is eventually consistent. And when you're doing writes, you should interact only with the overlaying API. For example, if it's lakeFS or any other solution, you interact only with the overlaying solution of, like keeping some kind of like branching model specifically that you're writing, and it should be eventually consistent. I would say like 2 layers of eventually consistency, because again, you have some kind of like transactional model probably of committing to a branch or something like that, I presume.
Yeah, and this is actually like the main reason why we never rely on the underlying storage for metadata at all. Like some operations, like the simplest operations on S3 are consistent, are strongly consistent. If I write to an object that hasn't been written to before, and I try to read it, I'll immediately be able to read it. That's like one of the guarantees that they do provide. I might try to list it, like its common prefix and not see it, and that's something that's like very common. But since we do that on top of Postgres, we do get a strong consistency as well. So like S3 or whatever storage you're using plays no part in the consistency of lakeFS. As long as the underlying bucket said, okay, like your write was persisted, and that's the entire role of the bucket underlying as part of the consistency story. And like all the transactional model on top is basically on lakeFS only. We had like initial thoughts of maybe delegating some of that work to S3, but we just simply never want to rely on something that's out of our hands, out of our control.
And there's another question in the chat from Troy. Can you also like address that?
Sure. So Troy is asking, so in practice for dealing with multiple lakeFS branches, we need one set of Hive tables for master and another set for any branch I create. Is that right? So yes and no. It kind of really depends on how you use lakeFS. We have a utility that's kind of part of the lakeFS installation for syncing different branches into Hive tables. So if you're using like Glue Data Catalog or Hive Metastore, you'll be able to take like, this is my existing table on master. This is my branch which now has a change. Please create like a copy table just reflecting that change. Point to whatever partitions weren't changed on the original table and just reflect those new changes on new partitions, if that makes sense. The other thing we can do, and this is something that we also support, is that since the data itself does get written to S3, we use something that's kind of similar to what Delta does, which is to create kind of symlink files. This is something that like the Hadoop ecosystem supports, where instead of creating like a partition full of Parquet or ORC files, we create a partition that has a single file called symlink.txt, which points to our underlying storage, to whatever objects we actually written underline. And this way you can like very cheaply create a new table that's actually for a given, even a specific commit. And then you can use it even inside Athena, which doesn't talk to lakeFS, to query a specific commit or a specific branch. Kind of a neat little trick.
Another question. So if a user starts using lakeFS, but then wants to migrate the data somewhere else, or maybe wants to stop using lakeFS, like, is there a way to export?
Yeah, absolutely. So like there are 3 distinct ways I can think of to get your data out of lakeFS. The simplest one is assuming everything is fine and your lakeFS installation is alive and well. Because we support the S3 protocol, you can even use something like DistCP or whatever tool it is you're already using to copy data from like one bucket to the other or from one prefix to the other, to copy from a lakeFS repository to whatever other bucket you want to be using, which is like outside of lakeFS. The other thing we do is that we let you create like a manifest file. Then we have like a lambda job. And what it does is that even if you like decided to delete lakeFS entirely and if you accidentally destroyed your RDS instance as well, if you take that manifest file and you say what branch you want, there's a lambda function that like wakes up, takes that manifest file and just copies the files from a specific branch or specific commit into another S3 location. So that would be the second one.
And if you want to actually, is there a way to preserve any of the versioning information, like to copy over to, say, Delta Lake or Hudi or Iceberg, preserving some of the versioning information?
So from that, I guess it's kind of like, it depends on your application and how your data is laid out. But since you can pretty easily interact with lakeFS from, say, Spark or any other compute framework, you can write whatever code you want to, like read Parquet or whatever from commits over time on lakeFS and translate it into a Delta or Hudi or whatever other format you want. But like, we don't have any native tool that does it for you because it really depends on the specifics. Okay, so another question from Troy. Guy asked about compatibility with Minio. So I tried to address it before, maybe it wasn't completely clear. So like, we theoretically support Minio, which I know it's kind of a crummy answer. That means that like, we've done some manual tests before because it is compatible with S3, so it should work. We don't have it as part of like our system testing suite right now, but we'd love a contribution around that. So if you're eager to contribute and you're using Minio, that would be a great contribution to have.
Okay, any other questions, people? Because we're over time, but still we have time maybe for one last one. Okay, you can also contact us, by the way, on LinkedIn probably, or on every social media and ask questions freely. I also added here in the chat link to the Facebook group of Big Things. We will post the slides and also the recordings of the YouTube itself there, and we'll post that on social media also, so really feel free to join. And really thank you very much to Oz and all of the other guys joining. Really interesting subject, and I think it's quite a thing right now of doing a lot of manipulation on data, specifically on data lakes, etc. And I really hope you can contribute, to all of you people, to contribute to the product itself, and try to form a real community around that, and try maybe to leverage some kind of abilities that you'd like to see also in different kinds of tools that integrate to that. So thank you everybody for joining. Stay safe, and there's like crazy times right now. And I hope to see you face to face sometime in the next future. I don't know, like a couple of months. Thank you. Bye bye.
Thank you,
Thank you, Oz. Thank you very much.
Thank you, guys.